A particular household uses 2 kilowatts heater, a 2 kilowatt heater for 2 hours per day, 4 95-watt light bulbs for 6 hours per day, 3.1 kilowatt electric stove element for a total of 1 hour per day, and miscellaneous power amounting to 1.5 kilowatt hours per day. Okay, so if electricity costs $0.105 per kilowatt hour, what will be their monthly bill assuming a 30-day month? Expressing your answer using two significant figures. Okay, so this is basically just going to be dimensional analysis and accounting, both of which are important, though not always the most exciting. A particular household uses 2 kilowatts per day, so we'll do 2 times 10 to the third, and then that'll be watts times 2 hours per day. Okay, so we have a 2 here and a 2.1 times 10 to the third there. 4 times 95 watts for 6 hours per day. 495. Okay, no 10 to the third. A 3.1 times 10 to the third watt for 1 hour per day. And we have a miscellaneous 1.5 times 10 to the third watts for 1 time per day. And then for the 10 to the third here, that's just what this kilo means here. That K means 10 to the third in this case. So what I'm going to do then is I'm going to convert this 4 times 95. So we'll do 4 times 95. We get 380. Okay? So this is going to be 0.380 times 10 to the third. So that way I can convert everything into 10 to the thirds. Hours per day. So we'll do, move the calculator over. So we'll divide that by 1,000. So 0.38. So we'll do 0.38 plus 2 times 2. Oh no, I gotta do that. 0.38 times 6. Okay. Whew. Better accounting. Okay, so 0.38 times 6. So this is 2.28. Okay? 2.28. And this will be kilowatts per day. So I'm going to convert everything into kilowatts per day just to get everything into the same units that's kind of similar. So the idea here is for these 4 95-watt light bulbs, when you have 4 of them, it's the same as having 380 watts per 6 hours per day, times 6 hours per day. And so when we convert that into a kilowatt, it's 0.38 kilowatts that's then used for 6 hours per day. So that's the same as 0.38 kilowatts times 6, which is 2.28 kilowatts used per day. So we're all trying to convert everything into kilowatts per day. And I know I'm playing kind of fast and loose with my conversions here. So this will be, I can do that one in my head. So this will be 4, the top one, 2 times 2 kilowatts per day. There we go. Coming down, we have 3.1 kilowatts per day. And then we have 1.5 kilowatts per day. Okay, now we're going to add all those up. And we have 4 plus 2.28 plus 3.1 plus 1.5. 3.1, 1.5, 10.88. So we have 10.88. And this will be kilowatts per day total. Kilowatts per day. Okay. So I have a lot of stuff here. Make sure that all seems reasonable. 1.5, 3.1, 2.28. So the only thing we really had to convert was the water heater, which was used for 2 hours per day. And then the light bulbs, which we had 4 of them. So 4 times 95 times 6. So 4 times 95 times 6. So give me like 2.28. 2.28, yep. So that seems reasonable. Whoop. So the last part that we care about right here, I feel bad about getting rid of all that. So let's see here. 4, 7.1, 8.6, 8.6 plus 2.88. 4 plus 2.28 plus 3.1 plus 1.5, 10.88. Okay, I probably did something wrong with my math in my head. 4.6, 8.6. Yeah, 10.88. I'm good at this. So we have 10.88 kilowatts per day. So from here, we know that we have an electricity cost, or an electrical cost, of, kilowatt hours per day. Good call. So I'm going to rewrite this just so it's a little bit more obvious. 10.88 kilowatt hours. I'm going to put an R on the hours just to feel good about myself. Per day. And we'll multiply this by 30 days per month times $0.105 per kilowatt hour. Kilowatt hour. Okay, there we go. So looking at the canceling, cancel, and we have 10.88 times 30 times 0.105 gives us 34.272 $272 per month. And we want to look at it using two significant figures, 3, 4. This would be $34 per month. So that's the idea of how we would go about for this problem right here. I will take this, move it over here, straighten it out a little bit, and then look at the second part. How much coal, which produces 7,500 kilocalories per kilogram, must be burned by a 39% efficient power plant to provide the yearly needs of this household? We should answer in two significant figures, and we'll go from there. Okay? So, I'm going to take our data that we had from here, that I crossed out. Tragic. So we know that we have 10.88. I'm going to rewrite this real quick. 10.88 kilowatt hours per day. And we want to convert this into kilograms of coal. Okay, so we have kilocalories per kilogram. So kilocalories, so calorie is a unit of energy, specifically the energy used to raise a calorie is a unit of energy to raise 1 gram of water 1 degree Celsius. So a kilocalorie, the K, would be 1,000 of those, or the amount of energy required to raise 1 liter of water 1 degree Celsius. And kilowatt hours is also a measure of energy. So kilowatt is a measure of power. So power is energy or work per unit time. And so when you multiply that by a time, which is what hours is, you get energy. So kilowatt hour is a measure of energy. Kilowatt is a measure of power. So it might feel like the kilowatt hour, like that hour on there, is extraneous or extra or means something different. It doesn't. So what the hour there does is it converts the power into a dimension of energy. So kilowatt hour, energy. So often measured in something like joules, but it can also be measured in calories or kilocalories. So I'm going to put the kilocalories on the bottom. So we have 7,500 kilocalories per kilogram. So I want to look up the conversion between calories and kilowatt hours. So let's see here. Whoop, whoop. The Google. And maybe here. Calorie. Calorie. Whoop. Calorie. Let's see here. Do we have kilowatt hours? Aha. No. If I look up kilowatt. Aha. 1 calorie is 1.162 times 10 to the negative 6 kilowatt hour. Okay, I'm good with that. So we'll go for, let's see. Hup. Nope, back to here. So we'll convert this. So 1 kilocalorie. Ah, that's terrible. Kilocalorie per 1,000 calories. 1 calorie is, go back to the Google or the Wikipedia, 1.162 times 10 to the negative 6. 1.162 times 10 to the negative 6 kilowatt hours. Nope, I'll rewrite that as HR. So now we got kilowatt hours. Perfect. So now we need to start doing some of our conversions, or cancelings, I guess. Does this give us, so we have per day here, and then we'll want 365 days per year. And this should give us, so this will cancel, that'll cancel, this will cancel, that'll cancel, that'll cancel, this will cancel, that'll cancel, this will cancel. And we're left with kilograms per year. So we haven't taken into account the efficiency yet, so we can't forget about that. So we have 10.88 times 365. I'm going to move this 10 to the negative 6 to the top. You can move it from the top to the bottom by the 10 to the negative 6. So dividing by 1 times 10 to the negative 6 is the same as multiplying by 10 to the 6th. So I'm going to put that on top. I'm going to write this as 75 times 10 squared, because there's 2 zeros. I'm going to multiply that by 10 to the third, because kilo, that's 1,000 is 10 to the third, times 1.162. I think that's all. Okay. So now we'll start canceling a little bit more. So this will be 10 to the fifth, which will then just leave that as 10. And I think that's something I could probably put in my calculator at this point. So we have on clear 10.88 times 365 times 10 divided by 75 divided by 1.162. Yeah, I'm good with that. So 455.67 kilograms. Okay? And now we were also told that it's only 39% efficient. And so to take into account that efficiency, we're going to need more coal. So the way we'll take that into account is we'll do 455.67 divided by 0.39 divided by 0.39. Click. And that gives us 1168. 1168 kilograms. Okay? So you're answering 2 significant figures. Oh, okay. So 1168, that would probably round to 1,200 kilograms. So 1,200, and the units then will be kilograms. How much coal will be burned? Provide yearly. Yes. Yep. So 1,200 kilograms of coal should be the answer. Unless I missed a number somewhere. There's a lot of accounting in this one, so I probably did. Maybe did. We'll see. So that's how I would approach this problem. To backtrack a little bit, this is almost all dimensional analysis, and it's basically trying to convert one to another. And the way I do that is kind of referred to colloquially as like the railroad track method, where you have a top, you have a bottom, and then you try and cancel out everything except for what you want. So that's how I approach this problem. Hope that helped. I will see you guys next time.